Hey guys, today I want to present a solution to the Turkey Math Olympiad 2021 problem 5. At first, let's have a look on the problem statement. We have given 4 positive integers a, b, c, d and the set S, which consists of all prime numbers p, such that we can find a positive integer n, such that p divides a b to the power of n plus c d to the power of n. Now we have given that the set here is finite, and we shall prove that b is equal to d. At first, I want to give the prime numbers in these set names. So let's write S is equal to p1, p2 up to pk, where p1 up to pk are pairwise distinct prime numbers. Here I want to note that if we can find a prime p such that p divides b and d, we can also work with b divided by p instead of b and d divided by p instead of d, and then the size of the set S decreases by at most 1. Since b and d only have a finite number of common divisors, the set S decreases by only a finite number if we repeat this step with dividing b and d by a common prime divisor, and therefore we can assume without loss of generality that b and d have no common divisors. For the sake of contradiction, I want to assume that b is not equal to d. This means that since b and d are both positive integers, one of them cannot be equal to 1. Therefore, if n is really large, the expression ab to the power of n plus cd to the power of n must be also large and is especially unbounded. So for really large n, we can find a prime p from the set, since the set is finite, such that this prime divides ab to the power of n plus cd to the power of n in a high multiplicity. Now if we choose two different positive integers, n1 and n2, such that they are close to each other and both really large, we see that the both expressions here are quite similar. Therefore, it seems unlikely that the same prime from the set here divides these two expressions in a high multiplicity. So let's have a look what exactly happens in such case. So we want to choose n1 large, and we want to have n2 equal to n1 plus s, and here we want s to be small. We now assume that we can find a prime p from the set S here, such that p divides the expression there for n1 and n2 in a large multiplicity. So let's write this down. Here we can conclude that p to the power of r must divide ab to the power of n2 plus cd to the power of n2 minus a multiple of this term here, and here we want to choose the multiple b to the power of s times ab to the power of n1 plus cd to the power of n1. We have chosen the exponent s in such a way that ab to the power of n2 minus b to the power of s times ab to the power of n1 cancels out. So we get that this is equal to cd to the power of n2 minus b to the power of s times cd to the power of n1. This is equal to cd to the power of n1 times d to the power of s minus b to the power of s. Now we see that if we choose s in such a way that s is bounded, and with the assumption that b is not equal to d, this term here, d to the power of s minus b to the power of s, can only be divisible by p by a finite number of times. Moreover, c is also divisible by p by a finite number of times, and therefore, if R is unbounded, at some point p must divide d to the power of n1. Let's recall that we had that the greatest common divisor of b and d is equal to 1. This means that if p divides d, p cannot divide b. But now we have that p to the power of r divides this expression here, and we know that since p divides d, p must divide d to the power of n1 at least n1 times. This means that a must be divisible by p to the power of the minimum of r and n1. But since r and n1 are both unbounded and a is a constant, this is impossible. At this point, we figured out the main idea to prove our problem. And it's now left to find concrete values for n1, n2, and r. At first, we want to have a look at s. Maybe we can choose s less than or equal to k, because then for some large n, we can choose n1 greater than or equal to large n, then we can choose n2 greater than n1, and n2 less than or equal to n plus k. Here we have k plus 1 possible values in this interval, and since we only have k different prime numbers in our set S, we can end up in such a situation here where we find a prime number p such that p divides these two expressions for different exponents n1 and n2. In our next step, we want to focus on the r. But since we have k different prime numbers, we need exponent r for every prime number. So we say we have the exponent ri for our prime number pi. Let's recall how we get a contradiction in this case here. At first, we know that p can divide d to the power of s minus b to the power of s a finite number of times because s is bounded by k. So our first summand for ai is the maximum of nu p of d to the power of s minus b to the power of s for all 1 less than or equal to s less than or equal to k. Then p divides c only a finite number of times, namely nu pi of c. In order to get that p divides d, we want to have ri to be greater than this term here, so we add a plus 1. To get the contradiction, we now add also a plus nu pi of a, because then we know that p to the power of ri cannot divide ab to the power of n1. To make sure that this is really a contradiction, we want p to the power of r to divide d to the power of n1. Therefore, we now choose n at first in such a way that capital N is greater than or equal to the maximum of r1, r2, up to rk. So far, we have no reason why we really should find a prime number p from the set here, such that pi to the power of ri really divides this term here. And therefore, we want to make another bound on capital N, namely capital N should be larger than or equal to p1 to the power of r1 times p2 to the power of r2, and so on up to times pk to the power of rk. This implies that a b to the power of m plus c d to the power of m is greater than or equal to the product from I equal 1 to k of pi to the power of ri for all m greater than or equal to n, because b and d cannot be both equal to 1. If now there exists no I such that this term here is divisible by pi to the power of ri, we get a contradiction by size, because this term here is only divisible by the primes from this set here. This means that for every integer in this interval here from n up to n plus k, we can find a prime pi such that pi to the power of ri divides this integer. And now, since there are k plus 1 integers in this interval here, we indeed can find n1 and n2 such that we are in this case here. By our choice of ri and our previous arguments in this case here, we then get a contradiction, and therefore our assumption that b is not equal to d must be wrong. The proof, as you would write it down, can be found on our website and in the description of the video. And now we are done.